Alright, so today we're covering the 2012 past paper question, question 22. This is covering module 6, inquiry question number 3. So Faraday and Lenz's law. You have a magnet that's placed on a sensitive electronic balance as shown in the diagram. A hollow solenoid is held stationary such that the magnet is partly within the solenoid. That's the diagram we have here. The solenoid is then lifted straight up without touching the magnet. The reading of the balance is changed. The question is, or the very first question, why does a current flow in the solenoid? So, as the solenoid is moved, there is a change in magnetic flux. Okay, now according to Faraday, Faraday's law, a change in magnetic flux will induce an EMF in a conductor. That's how you answer that one. Cause and effect right there. Question B. Explain the reason for changes in the reading on the electronic balance as the solenoid is removed. Let's have a look. So we have a north pole, and so the poles or the magnetic field always goes from north to south, okay? Which means the poles, if they're drawn like that, is coming out like this. So it's kind of bursting out, okay? Just gonna erase that, and I'm gonna draw it on the side just so the depiction is a bit easier. So from the magnet, this is the kind of orientation of magnetic fields the solenoid is facing. As you move the solenoid away, so as the solenoid is being pulled away further up, you have fewer magnetic field lines going up as well. Okay? So according to Lenz's law, we want to counter this. We want to ensure we have enough field lines as we did before. So the magnetic field induced, at least at the corner of where that solenoid is to produce more fields going up. Okay? So if you use your right hand grip rule, going up, or your right thumb pointing up, that means that this north pole here, or at the top, it's a north pole, and down here is a south pole. What that tells us is that there's going to be an attraction force between the south pole of the solenoid. So solenoid's here, it's the south pole, and as it's going further away, there's going to be an attraction force towards the north. So thinking about that, that's going to drag the pole or the magnet up. And as you drag an object up, there is less normal force experience on it. So that means there is a drop in the balance in terms of the mass. Once you've taken this solenoid really, really far away, there is no longer any change in magnetic flux. Hence, it will go back to the original mass of 42.42 grams. That's the explanation like that. Let's put that into numbers or explanation. So the first one is a solenoid moving away from magnet. So what's actually happening here? The mass, 42.42 grams, will decrease. So it will go down. Okay, so that's the first thing. The reason being is due to the change in flux a back EMF is induced, which creates a current which induces a magnetic field to oppose the change or the original change. In this case, a south pole is induced at the bottom of the solenoid. This creates an attractive force, pulling the north pole up, reducing the mass on the electronic balance. And then the next part is when it's entirely removed. So solenoid completely removed. When that happens, mass returns and stays at 42.42 grams. Okay? And the reason being is because, or the reason why it will stay there is because there is no change in flux. Ran out of space. So, let's draw that out again. So, no EMF induced, no change in flux, no induced magnetic field. And that's how you explain the question there. Obviously, that's a little bit longer than what I initially intended, but that's kind of the explanation of the whole question, if that's what you were seeking. Anyhow, that's how you answer the questions. There's a couple of playlists there if you want to look at some other videos to explain. Mr. Wong, have a good day.